Hello, my name is Luis Acosta, along with my other team members, Brian Camacho, Ethan Floor, and Patrick Perez, and our product owner, Professor John K. Babani. We're here to present to you our machine learning optimization project for summer 2020. So the overview of the problem is that as we get increasingly more demanding programming tasks being thrown at us because of, for example, huge data center tasks, large data processing tasks, DRAM is increasingly becoming a bottleneck for a lot of these issues. Since it's the main working memory in most computer systems, anything that we can do to extend it at a cheaper cost will usually get pretty good dividends in performance. And one of the things recently that's come along as an opportunity for this is that persistent memory technologies have actually gotten much better as far as memory access speeds, and in particular, they're still quite cheap in general. So one of the things that you can do is that you can actually augment DRAM by tacking on persistent memory in the same memory tier. So for example, we would normally have had persistent memory, for example, in the form of an SSD, in a memory tier just above or below, depending on how you want to look at it, DRAM itself. But what you can do is that you can actually extend DRAM memory addresses with persistent memory. Now, it's still about an order of magnitude slower, so you're still going to have some pretty slow accesses overall. But the idea is that with some careful memory management, we should be able to extend the effective DRAM that we have and not suffer too much of a penalty to actual processing speeds. So this goes into our project, which is we're trying to develop a simulation environment to test various different reinforcement learning algorithms, specifically on how they manage memory, and to see if we can get a pretty good memory management scheme and improve upon some existing ones based on the discoveries of these reinforcement learning algorithms. So here's some primary user stories that actually get into some of the brunt of our work. These are not by any means exhaustive of everything that we did, but they're pretty explanatory. So one of the things that we wanted to do is, as hybrid memory researchers, we wanted to figure out ways to actually, one, improve system performance, but two, figure out which reinforcement learning algorithms would actually help us in this task. Not all reinforcement learning algorithms are built the same. Some of them are built for entirely different types of data entry. So for example, discrete action spaces versus continuous action spaces is one way of thinking about it. For us, we have a discrete action space. Hybrid memory technically has pagination that are discrete. So there's one page and then the next page is not really page 1.5. We treat those as units. However, there's a lot of them, so we can also think of them as continuous in a certain sense. So these are just some of the things that we had to work out. On the second user story, as an environment engineer for hybrid memory, we needed to figure out how to represent in a data structure the actual hybrid memory system. So for example, we can't just represent them as the same pages because the DRAM has faster page accesses. By contrast, the persistent memory has slower page accesses. So we need to figure out some sort of data structure that represents this. And not only that, but it actually supports us in taking memory trace inputs that actually show, for example, over the course of a program, what pages were actually used and what pages were not very frequently used, and basically get an idea of each page, when was it used, frequency of use, and then be able, again, to feed all this into a reinforcement learning algorithm, which has its own unique requirements. And then lastly, as a reinforcement learning engineer, we want to be able to identify a reward function that meets our needs. Reinforcement learning basically requires a reward function to tell the agent that's learning whether it's doing a good job or not doing a good job. So careful crafting of that reward function is pretty key to our success. So just some system overviews are, we really have kind of one input and one output. The one input is a persistent page trace file. It could take any number of forms, but what we actually did is we took the Yahoo Cloud Serving benchmark. These are open source files that just show standard server loads. And they're text files. They literally only have page ID and time accessed, and tens of thousands of these page IDs and time access. So they're kind of a sequence trace of the memory activity on any given server load. And then the output are these trained reinforcement learning models that we can save and then reuse at a later time to either refine or to glean ideas from about proper memory management and use. As far as security and privacy, there's really no direct data taken from users, no direct data outputted either as far as private data. So here's a rough use case diagram for the overall system. On the left-hand side, you see the user, and the user we think of generally as something of a data scientist or other AI researcher. And what the user does is that they interact with a reinforcement learning agent, setting parameters from among any number of different reinforcement learning algorithms. So that agent gets populated with implementations for those reinforcement learning algorithms. The user sets a series of parameters, and then what the user does is that they input a data, right? So in our case, a memory trace into the environment that we came up with. That was the most of the project, right? And we were able to use that to feed reward information to the agent based on the memory traces, because again, there's a reward function that the agent abides by that it gets from the environment based on the possible actions that it can take at any given state. And this allows it to determine whether it's progressing in a good manner, which is to say increasing the efficiency of memory or decreasing the efficiency of memory. And all this ties into a series of interfaces from OpenAI Gym, something which I'll get into later, but we used OpenAI standards to make sure that one, we can slot this into existing software packages, two, we can pull from existing libraries, and three, we don't reinvent the wheel in a lot of very basic functions. And then the other major case, user, as it were, is the developer, right? The developer is responsible for the actual ruminant environment, for the way that the reinforcement learning agent is structured, as well as for populating the reinforcement learning algorithms. So here's a sequence diagram that more or less shows you the same thing. The idea is, again, the primary user, so a data scientist, would be seeking to initialize an agent, making certain user selection on parameters. All those selections get sent over to our machine learning algorithm libraries, which directly accesses OpenAI Gym libraries. So they get those resources and they populate a series of objects effectively. Those get returned, the requested resources get returned, the requested model gets returned back to the reinforcement learning agent, which then populates the agent. And at this point, you can actually even stop if you wanted to. It's not necessarily a continuous project. You can actually stop here with a baseline agent that knows nothing, but is a baseline from which you can learn from based on certain parameters. So from there, you can continue onward though. You can run the agent and tell the agent to get information from the environment. The environment data will kind of come back and forth. What will happen is that the agent will take a step. It'll perform some sort of action. It'll calculate its rewards for any given possible actions from here on out. And then it'll go back into the environment, recording and making note of the rewards that it has. And then it'll take the next step, and so on and so forth. And there's a little bit of exploration, which we basically use to make sure that we don't hit a local maximum, and instead we're looking for that ever elusive global maximum for the reward function. As far as the architecture itself, so again, it's pretty simple. Really only has a single input as the memory traces, and then there's a user input, which mostly goes into the modification of parameters and the selection of the algorithms. So some small pre-processing is done on the memory traces just to make sure that it is able to run in our ruminant environment. Again, puts into data structures, mostly Python dictionaries is what we ended up using. And then the reinforcement learning agent gets fed data from the environmental simulator. So one thing that I want to know is that OpenAI Gym supports all this because it basically has a series of interfaces. They're not really interfaces in the object-oriented sense, but they're effectively standards by which you meet. And then if you meet these standards, you can use OpenAI libraries that support these already implemented functions. So it's almost like an agreed-upon interface. The actual deployment itself can take place in a single system. A lot of the back-end calculation of this stuff is done in a package called TensorFlow, which is something that Google open sourced pretty recently, and it's very extensible. You can even do it off GPU. There's TensorFlow GPU support. So if you wanted to scale this up, there's actually nothing stopping you because the backend is all taken care of by a package that would normally use be used in things like data centers. So that's perfectly scalable. But for our purposes, for these relatively small demonstration purposes of setting up the environment, we really have really a single machine that you can effectively use both in the development environment, the data environment, and the actual user environment. So for our purposes, we really just focused on effectively a single system, a single PC or laptop if you really wanted to. And then here's an actual look at the class diagram itself. So as I said, OpenAI Gym has a series of agreed upon standard functions, which if you implement properly, allow you to access other library functions that use them. So all these functions are effectively an interface that gets implemented by our environment, which is our custom environment here that we wrote. So in particular, so as I told you, in pre-processing, memory traces will get processed into a memory trace data frame, which is a part of the pandas library, and it's just a very optimized data structure that has a lot of good qualities for it if you want to do things like linear algebra, which as a matter of fact you do in general if you're doing any type of machine learning. And then there's also other OpenAI structures, specifically action spaces and observation spaces, which you can think of as action space is the list of all possible actions that you could take. Observation space is the list of all possible observations that you have at any given step. And then this is just reinforcement learning terminology. And OpenAI already has sort of agreed upon standards for what those should look like, and we actually pull from those. So that's this space is discrete and space is multi-binary. In addition to that, we have a bunch of helper functions that help initialize the entire environment. We have these implementations of these OpenAI Gym agreed upon functions that allow us to function within the OpenAI framework. And then in addition to that, we have a series of helper functions just to maintain the actual the play, as it were, the small little details of the environment that actually have to be tracked so that we can feed that into the agent. So the idea is we can take the environment, we can feed it 1 to n, so a single environment can support up to n number of agents all learning at the same time, either in parallel or sequentially, as the case might be. And then the agent has a series of parameters, so these are all machine learning, reinforcement learning parameters, has a series of actions, so things like requests to the environment, what the action is, requests to the environment, what the next possible state will be, et cetera, et cetera. And as I said, a lot of the backend stuff on agents is done by TensorFlow libraries. So we can basically have these backend optimizations for these very complex and sizable machine learning tasks. In this particular example, and for our testing purposes, we use what's called DQN, which is Deep Q Network, which is a specific type of deep neural network that implements reinforcement learning. Our actual environment itself is sort of agent agnostic, as long as it's a reinforcement learning environment that implements the OpenAI standard. In theory, you could use it for just about any particular agent implementation. But for our testing purposes, we use DQN extensively. And then each agent, as it conducts its actions, will get its reward calculation based on our carefully selected reward function. Those get fed back into the environment when it takes the next step. And this is a lot of the algorithm I kind of described already, so I'll just go into some of the details of Deep Q network algorithm. The idea is, one, we initialize a replay buffer memory. So one of the things about Deep Q network algorithm is that it doesn't just take its own next step or the previous step into consideration. It actually has this large memory bank that it can pull the last R number of steps, 1,000, 10,000, whatever the case might be. There's another parameter that we can mess around with to get better performance. And it'll basically use that memory to figure out whether it made a correct step in this latest step. But initially, it's just effectively 0 because we haven't actually taken any steps yet. And then we initialize a Q function. So this is the deep Q part of the deep Q, or I should say the deep network part of the Q algorithm. Normally in a Q function, you can almost think of it as a table, or an Excel document if you sit there and think about it, right? You have an x-axis and a y-axis. Normally in the Q function, the x-axis is the state, and then the y-axis is the action. And then the cross product of all those possible state and action combinations get calculated via our reward function. So you can think of it as a giant lookup table. A normal non-neural network version of the Q algorithm is effectively a giant lookup table that we populate by taking steps and actions. The neural network version of this, though, basically says, the action and observation spaces, based on what we have, is just way too large, and we can't possibly encapsulate that in memory. Not very well, and we have to use an awful lot of memory. So instead, what we can do is that we can take a neural network, we can seed it with some random seeded starting weights, and then we'll get it to look, or we'll get it to get an input and output effectively like what we have with our lookup table. So if you think about a lookup table, the input and output for a two-dimensional lookup table is the x coordinate and the y coordinate, and the cross product of that is the output. So the state action matrix will get our state and action reward for any given state and action. And instead what we're doing is we're training the deep neural network to simulate that table. So for any input, state, and action, the deep neural network will be populated in such a manner that the output of the network will be the reward function for that given state and action. So that's sort of step 2 as far as initializing, but this is just random right now. We haven't really populated it yet. And then we also initialize what's called the target Q function, and the target Q function is just there as a kind of best guess to figure out whether we're heading in the right direction. And because we're constantly updating the Q functions, we also need to basically rebase every now and again to make sure that we're not too terribly off track, or that the gradient descent that we're trying to perform to get to an optimized Q function that mirrors our target Q table is not just going off in wild tangents that don't actually do what we're trying to have it do. And then in the actual learning loop itself, it's actually 2 nested loops. So I'll start with a sequence. A sequence is, for our purposes, a memory trace. So it'll go through the entire memory trace of pages accessed at this time with this frequency. And then for the number of times that we want to do is the episodes, sometimes also called the epochs, because sometimes you might need a couple of training iterations for the reinforcement learning algorithm to actually figure out what's the data behind, or I should say the patterns behind the data. So going into the actual learning loop itself, so one of the things that we do is that sometimes we just take random actions. These are called exploratory actions, and we can set that with the epsilon parameter. And we find that actually sometimes that's actually very useful. Otherwise, we just basically take a selection of the possible rewards based on the next possible steps that we can take, and just select those, or effectively sample those based on maximal reward and select the one that gives us the maximum reward. We take the action, we observe the reward, so we actually jot down the reward, because previously we weren't really jotting this down. It's just too much memory space. And then we set the next step as the current step, and that's effectively we've taken the next step at this point. And then we do some housekeeping tasks. So we store the transition info into the replay memory, which we initialize with nothing, but now we basically take a memory of the step that we took and we put that into the replay memory. We'll take a sample of some random transitions just in case there maybe wasn't something better, or we'll also stick that in the replay memory usually. Depending on your implementation of the deep Q network, you could or could not do that. And then we'll go into the gradient descent. So the idea is we'll go back into our Q function and we'll start messing around with these random seeded weights. And we'll start basically putting them in a manner that shows the most improvement to moving to our target Q function. The idea of it being that after we do enough of these steps, we'll be able to simulate our Q table via our Q function via carefully selected weight distributions. And then every now and again, we're going to reinitialize the target Q function just to make sure that, again, it's not going off on some wild tangent and it's actually getting to what we think is the best guess of where it needs to get. So here's our reward function. You can think of it as a stepwise function. The top one, so whenever it's given a positive reward, this equation basically just represents if the efficiency of the DRAM is, the efficiency of use is increasing. The next step represents whether the efficiency of use of DRAM is decreasing. And then the last step is whether there's no change. And we basically interpret no change as effectively a a loss because we're trying to get constant improvement. And then these two equations, just both are kind of there to tell you that the maximum and the minimum total reward will be within about the same order of magnitude. And then here are some results. Again, our target for this project was actually to deliver an environment, not necessarily to deliver researcher results, but in order to test it, we do actually need to figure out, hey, what are some of the things that we can possibly put in there as a user, and then as a user, we'll get out these results. So are the results basically making sense? Does our environment work? Do we test it properly and debug it properly, etc. So we actually ran it. Again, this is deep Q networks is what we did, and we did some things like hyperparameter tuning, so exploration probability, which is that epsilon that I was talking about when I was talking about the algorithm. You can see that there's actually a fairly interesting distribution, a symmetrical distribution around half exploration. So this is half the time take the proper action, half the time take proper, best rewarding action. Half the time take an action that doesn't necessarily reward you best, it's just a random probability action. One of the interesting things that we found out here is that 0.2, so relatively little exploration, you seem to maximize reward, and then this kind of cut off here, but this is actually at 0.8. At relatively high exploration rates, you also get a lot of reward. Exactly what this means, we're not sure what insights this gleans us, because we're not really AI researchers, we were just setting up the environment. But we think it's at least interesting to know that there's some sort of interesting symmetry here. And then this is another measure. This we're measuring in the x-axis, the exploration probability, so same x-axis measurement as we were taking here. But instead we're taking the temperature difference, which is to say the difference in efficiency between the DRAM and the primary memory, or the persistent memory rather, because we're measuring those two different memory tiers. This looks like it's a lot of variation, but if you look at the overall magnitude, it's actually not that much difference exactly. So what we find is that even though we do get better reward calculations for certain probabilities, it's not significantly different in an overall level of magnitude. So these are just some interesting things that we did when we were doing our testing. Again, we're not AI researchers, so we don't really know what sort of deep truths this is telling us about hybrid memory management. But this is our testing results. At this time, if you have any questions, feel free to post a comment or otherwise get in contact with us. But my name is Luis Acosta, along with a couple other my compatriots, both in senior project as well as senior design capstone 1. We've been working on this project for this whole semester, and we'd like to thank Professor Bamani for kind of helping us along, as well as Professor Masood for sort of tailoring this whole experience for us. Thanks again.